which we found from optimization really leads to optimal operation or not. So clearly this and this correspond to disturbances, and here we see that they are being nicely rejected using these controlled inputs. On the other hand, we start with not the optimal set points, but we gradually change them. As you can see, there is a change here, there is a change here, and there is a change here. You will notice that these values are not the same. I was talking about 30 ppm, but I keep it 25, and this is the reason. And the reason why we do that is to keep a back off. And the back off is to make sure that if we have not so good control, it will still have the possibility to maneuver between 25 and 30, yet keeping below 30. There are some other variables that are plotted here, which is the oil holdup at the top, which is the fraction of oil going in, volume fraction of oil going into the reject stream, volume fraction of gas going into the reject stream, and volume fraction of water going into the reject stream. As you can see, as we move closer and closer to the optimal, which is here, here, and here, at this point after 4 hours, we see that the flotation gas usage is the minimum. And that clearly proves that our optimization results also work on closed loop simulation. At the same time, one important thing to note is that we start to see a gas holdup rise as we reach the most optimal point, which is between 4 and 5. We see the highest amount of gas holdup, and that clearly says that if we take more and more gas, only gas and oil out of the top, then we are not going to take. So this is apparently the optimal. Now I will talk about chapter 7, which is the largest chapter in the thesis, and here there are 2 major contributions. One is a coalescence-based gravity separator model, and then to combine all these models that I discussed into a separation system that I showed towards the introduction, and to analyze, make an analysis out of that separation system. Again, the major goal in the separation system is to maximize the flow of water out of the system at the specified specifications of 20-30 ppm. So I will first talk about the gravity separator model. There are many gravity separator models in the literature. So why do we need another one? Well, none of the gravity separator models have coalescence being described in the simplest possible way. And number 2, many of the gravity separators do not quantify the oil concentration and water concentrations in the 2 streams in a spatial way. So they might have it in the lumped way, but I do it in a spatial way. So I'm going to touch upon that very quickly. So first, let me, for those of you who don't know what gravity separation is, we have well fluids containing a multi-phase oil, water, and gas coming into the separator, which separates into there is an initial separation that happens in this part, and then we see a layer of oil forming, a layer of water forming. There is some dispersed water still remaining in the oil, there is some dispersed oil still remaining in the water, which gradually moves upwards and downwards based on the densities. And towards the end, we have a little bit cleaner oil and a little bit cleaner water. Oil cleaner of water, water cleaner of oil. And then we have a gas outflow also. And this is the weir that stands in between separating the 2 flows. And we take the water outflow here, and we take the oil outflow here. To create this system, I discretized this gravity separator into first two parts. First is the initial or inlet zone, and the other is the main separation zone. I must mention here that this work has been done in collaboration with Sindre, who is sitting right here as a master student. I had the ideas, and he developed a simulation code for this, and then I worked on the optimization together with him. Here we discretize the system spatially in x direction as well as y direction, and we write down the mass balance again using the same equation that I showed at the start. And most noteworthy to see is that we have 2 different levels, the water level and the oil level. The oil level is describing the total liquids in the system, and water level is describing the water in the system. And we have inlet disturbances, the inflow of the gas at inlet pressure, liquid flow at with a specific amount of water in it. We have the gas pressure and the volume available for the gas, and we have the gas outflow. We have the water outflow and the oil in the water outflow. We have the oil outflow and the water in the oil outflow. Now, to describe a little bit more on how we developed the model, well, we first considered an initial saturation that this is the flow of the total flow that goes into the oil layer and the total flow at the inlet that goes into the water layer. And then we start to describe several different directions here. You can see the red ones are the movement of oil droplets crossing the control volumes in the water layer. So this is like a water layer, and this red line describes the flow of oil going upwards. Then we have the flow of water droplets coming down, described by these green arrows. And then we have the in general flow that is going, this is like, so in my thesis I described this flow as in the axial direction as the convective flows, and the vertical flows are the non-convective flows. But here you see also some vertical flows, and these are not non-convective, these are convective, because the overall here the water starts to come down here and go out here. Here the oil starts to go over the weir and starts to go up. One key feature of this work is also the coalescence modeling, which has been done using 10 droplet classes, and these droplet classes are contained within. So what that means is if you take 2 of these droplets, they will form the size of this, and these are real sizes. I made the plot with the right numbers. So if you take 1 and 2, they will combine to become 3. If you take 3 and 2, they will become 5. If you take 4 and 1, they will become 5. And what that means to describe, and this number 1 is 150 micron, and number 10 would be cube root of 10 times 150 micron, and cube root of 10 is roughly in the range of 2 point something. So we covered a range from 150 to 320 micron range, and we described this using chemical reaction kinetics, that 2 of these combine to become 1 of these. So the negative ones are denoted in red and the positive ones. So this is kind of the starting of the stoichiometry metrics, and of course it doesn't end here, there are many more equations. So in total there are 25 equations to describe these 10 droplet classes. The gravity separator model then results into a model with 3 disturbance inputs, 3 control inputs, and 3 control variables, and 2 other variables. And this is the most interesting part, where the model is able to describe how much water is going into the oil phase and how much oil is going into the water phase. And to now analyze not only the gravity separator model as well as the whole separation system, we did an optimization study, and the objective of the optimization was to maximize the outflow that is going out here, which is the water. So the idea is if we throw maximum amount of water at specified specification, then we have very little to take to the top side, which is beneficial. To do that, we formulate this optimization problem with model equations in the constraints. Then we have a lot of other constraints. The oil level is constrained between 2.2 and 2.5 because the weir level is at 2 meters, and we want to have a 0.2 margin. So we don't want the oil level to be any lower than 2.2, and we don't want the oil level to be any higher than 2.5, so as to leave some space for the gas. Similarly, water level cannot be below 0 and higher than 1.8, there again keeping a 0.2 margin from the 2 meter weir height. Our model cannot describe the situation where the water level could go beyond the weir height. Gas pressure is fixed at 8 bar. Flow split is considered to be the flow split is in the hydrocyclone, where how much we take out in the central part is between 1.5% and 2.5% of the inflow. The CVFU is considered to be maintained at 1 bar pressure, The ppm out is considered, the ppm that of water that is going out here is considered to be between 0 and 10 ppm. The gas holdup in the reject stream here is considered to be 45 and 55%. And the reason why we chose these numbers, because we, to be able to control something that is needs to be able to be measured. And here we make an assumption that the gas fraction measurement is possible accurately only between 25% and 75%, and to keep a 20% margin for those times when, because of imperfect control, it could go beyond the set point for a while, we keep it between 45% and 55%. And we have the other physical constraints also. So to study this separation system, I'm going to show the results. We analyzed the system for 3 different sets of cases. Case number 1, we have liquid flow of 2124 meter cube per hour, and water in that part as 15%. Then we increased by 10% the total inflow in case 2, and then we increased the water fraction in case 3. And this is a typical scenario in subsea or in any separation in oil field. There is very likely that at some point the separation system will have to go through a tie-in. When you tie in a different field or different well, and then all of a sudden the production goes high and the separation system has to deal with it. Also, very quickly the water content in the fluids also start to rise. So these are very plausible scenarios. So then we analyze the optimization problem for the 3 cases, and we find that here we have 3 degrees of freedom: how much water to take out, how much oil to take out, how much gas to take out. Here we have 1 degree of freedom: how much of the fraction of the inflow we take out in the overflow, which is the oil reject. And in CFU, I showed in the previous chapter, there are 3 degrees of freedom. So in total, 3 in gravity separator, 3 in CFU, and 1 in hydrocyclone leads to 7 degrees of freedom. Here we see that out of this, 1, 2, 3, 4, 5, and 6 are constrained at their constraints. So those are the ones we have to control at their constraints. That leaves us with only 1 degree of freedom that is not active. And let me talk about that degree of freedom, and that is the water level. All other constraints are active. And here I also show the different control variables in the gravity separator and the ppm in the outlet in the water outlet. I also have the hydrocyclone. Here I show how much ppm is going out in the hydrocyclone, and the flow split that we have. It goes to the lowest flow split. It was between 1.5 and 2.5. It goes to the lowest. I also mentioned the separation efficiency in the range of 90% for the hydrocyclone part, and which is computed as the ppm out divided by ppm in. Here we have the CFU pressure, the ppm out of the CFU, the gas hold up at the top, which is again at 55%, which is the highest limit, because keeping the gas fraction high is optimal, which we also saw in the previous chapter. Here we also demonstrate the separation efficiency, and I also quantify how much water we are able to throw out. Here it is 83% with a higher water in higher flow. Case number 2, we have a lower water that we are able to throw out, and in the 3rd case we have more water overall coming in, so this number goes a little bit higher. To put it in a nice way, I put this flow sheet where we have the gravity separator, hydrocyclone system, and the CFU system. These are the the disturbances to the system. I consider an 11 bar inlet. It's very low, but I can argue about that later. Then we have the pressure at 8 bar going out, and this is the gas which is used in the CFU for the flotation purposes. This water comes out at 264 ppm, which goes into the hydrocyclone system, which has a 90% efficiency, produces around 20 ppm of oil in water. Rest is the reject stream, which has 1 to 2% of oil content. Then we have the CFU system. In the CFU system, we finally reduce it further down from 19.5 to 10 ppm and make it suitable to throw into the sea. Rest is going at the top, which is the reject stream, which has maximum gas, a little bit of oil, some water, and it is at 1 bar pressure. The result of the coalescence is that we can estimate the concentration of oil droplets as well as concentration of water droplets in the oil layers in the different control volumes, and the oil droplets in the water layer. And here we see that as we go, this is the water level and this is the weir height. And as we go to the right, we see that these numbers are going down clearly because there is some non-convective transfer. The same happens in the oil layer where the water concentration is reducing. And as it reaches here, the coalescence is still working. That's why you see that the lowest number goes down further, even though there is no non-convective flow in this part. The oil is going further down quite a lot, and towards the end it starts to accumulate because in these areas we do not consider non-convective flow, because the convective flows are too strong for the effect of non-convective flows to be any more important. Separation system control structure. We have the pressure being controlled using the gas flow, the water level being controlled using the water flow, and the oil level being controlled using the oil flow. And then we have the hydrocyclone flow split, which decides how much to take here. And then we have the CFU, where we, compared to the CFU paper or the paper chapter number 6, the CFU article, we have a different control structure for the CFU here for a very good reason. We have the same loop for the pressure. We use the reject flow to control the pressure. We have the same loop for the concentration. We control the concentration using the flotation gas, but here we changed the control structure, and that we found as the more optimal compared to controlling the liquid holdup. Controlling the gas fraction at the reject stream is optimal. And this is something which is also implementable, because there has been some work in the CFU literature where there have been methods developed to estimate this gas fraction using acoustic methods. Now to the final results. I have the gravity separator results. Here this row demonstrates the 3 controlled variables: the pressure, the oil level, and the water level being controlled using the gas outflow, oil outflow, and water outflow subsequently. Correspondingly, sorry. We have some other things which are here. These are the disturbances, case 1, case 2, and case 3 demonstrated at different time points, and we see how this control structure responds to that. And we see that the pressure is very tightly controlled, the oil level is also very tightly controlled, whereas the water level is let loose a little bit and the control is very slow. And the reason is to make sure that the downstream equipment don't see it as a shock when there is a sudden disturbance change. Though disturbances in an oil field may not be of this step nature, but we just demonstrated them in the work, just to make sure that the control system is also able to handle those specific kind of situations. We also are able to see the nature in the water in oil content and oil in water content, as we can see that the separation load is increasing from case 1 to case 2. That's why the separation gets worse and these numbers become higher, which means they're more impure. The oil in water in ppm goes from 260 to 270, and the same case for case number 3. Further, we show some changes in the last 2 parts. Here we show some changes in the changes in the level set points, just to demonstrate the gravity separator a little bit more. Here we can also describe dynamically how these things, the changes in disturbances, case 1, case 2, and case 3, plus the changes in the levels in the gravity separator are affecting the concentrations within the gravity separator in different control volumes. I don't think I have time, but to discuss this. Then I talk about the hydrocyclone. It's very straightforward. The flow that is coming out of the gravity separator, the water flow goes into the hydrocyclone, and that forms the inflow, which is demonstrated here. And this inflow is of course rising because more and more water is coming in with the cases. And the oil in water is also increasing, but it is dropping a little bit here. And overflow, which is used, or we use a fixed flow split based strategy to control the hydrocyclones, and that's clearly reflected with the ratio proportional relationship between these two, and accordingly also on the other flow. And then these two flows are summed up to this one, or this is this minus this. Then we have the oil concentration in the overflow and the water quality in the ppm. So in the bigger superstructure I showed it's 19.5 to start with. It goes a little bit higher and further higher in the case 2 and case 3. And the final stage is the CFU, where the most important thing is that we are able to maintain this 10 ppm limit in all cases for all disturbances. And the gas holdup is maintained at 55% for all cases, and the pressure is maintained at 1 bar. So this is a fairly okay control structure to control this process, and it is able to handle all the disturbances that are coming from the upstream using these 3 different control inputs. With that, I would like to conclude my talk with some final words. We developed separator models for use in oil and gas industry, which predicts concentration in oil and in water. Simplified modeling approach demonstrated by this main equation at the start. We used the models, we demonstrated the utility of the models using optimization, mostly in part 3, control structure design in part 3, system analysis also in part 3, and a little bit on estimation of unmeasured variables in part 2, specifically chapter number 3. For future use of models, validation is necessary. And I also include a section about guidelines for modeling in the conclusion chapter, which is a very small but quite informative. I would like to thank you to attend this defense and open for questions.
Very good, Tamal. Thank you for the nice presentation. Now we give the word to the first opponent, but I know sometimes some audience members like to leave and get back to work after the presentation, so if you don't want to watch the opponent's questioning, you feel free to leave now.